Hi, my name is Istvan Sárandi from RWTH Aachen University, and today I will present you our latest research on 3D human pose estimation. In short, our approach can directly predict metric scale skeletons even under truncation and is based purely on heat map estimation. Through this learned scale estimation, we can also estimate the root joint position in a differentiable manner at state-of-the-art accuracy. But first, some background. In human pose estimation, we want to locate the body joints of a person shown in an image. This can then be used for human-computer interaction or human-robot collaboration or other things. We may want to do this in projected pixel coordinates or in metric 3D space. So how can we encode this information with a neural network? Early approaches directly regressed the 2D coordinates as one long vector of activation values in a fully connected layer. But convolutional nets are already inherently spatial, and so later methods showed that fully convolutional heat map estimation works better. Here, the position is encoded as high activation locations, not as values. In 3D, the direct coordinate estimation is exactly analogous. But what is the exact analog of heat maps? Here we highlight two main existing approaches. One uses location maps. Here, the long vector of coordinates is still predicted as activation values, but now at every position in the image. Then, 2D heat maps are used to read out the vector from the right place. Alternatively, the volumetric heat map approach represents the pose as high activation locations. The first two axes represent image space, the third is the metric depth, and this is called a 2.5D representation. Essentially, this reduces the coordinate estimation problem to many small classification decisions, one per voxel, which tends to be easier to learn for CNNs. So what are the benefits of each representation? Encoding coordinates as values makes it easy to produce metric scale output, and the predictions are also not limited by image truncation, which can be an issue if the input crop is not perfect. The output is also naturally continuous, but the representation makes no good use of the inherent convolutional structure. By contrast, 2.5D heat maps do not directly output the metric scale skeleton and need additional post-processing, often with strong assumptions and requiring the focal length. It also cannot predict anything outside the field of view, but it makes very good use of the convolutional structure. Due to the discrete grid, it's also often assumed that high-resolution heat maps are needed, but we will see that soft argmax can help with that. So how can we get the benefits from both of these paradigms? In our approach, we want a heat map representation that can directly encode the metric scale skeleton, not limited by the image bounds. Also, it should be simple and fast, even with low-resolution heat maps. So what exactly is involved in estimating a metric scale pose? The most important quantities are the person distance, the focal length, the projected size, and the metric size of the person. Out of these, the projected size is easily visible from the image. The metric size may be approximately estimated from an image crop. However, the person's distance would be much more difficult to directly regress on a crop, as illustrated by the dolly zoom effect. Similarly, the focal length is hard to estimate from just a crop, but it is often known and remains constant for a given camera setup. Therefore, we aim to directly estimate the metric scale skeleton by defining the x and y axes of the prediction volume directly as fixed metric sizes. We refer to this as a metric scale truncation robust heat map, or METRO for short. Note that here the input and output of the fully convolutional network are no longer spatially aligned. We show, however, that somewhat surprisingly, the mapping can still be effectively learned convolutionally. We use a simple architecture to be able to concentrate on the representation itself. Taking any off-the-shelf backbone, such as ResNet, we directly regress the heat map by a 1x1 convolution without any additional learned layers. We obtain continuous coordinates through soft argmax, giving us a root relative metric pose. If we want to estimate the distance as well, we use a 2D heat map head and perform a differentiable reconstruction of the root joint, yielding absolute poses, which we can then supervise with an absolute loss. We call this combination METRAPS. Let's see the results. On Human 3.6M, we get state-of-the-art results, and our method performs better than the 2.5D baseline, which assumes constant bone lengths. The results under truncation are especially interesting. Here we can see that the model can reasonably estimate body joints outside of the image bounds, outperforming prior methods. Here we show one heat map and the full predicted skeleton within the heat map. We can see that the predicted skeleton remains roughly the same size, even when the image is scaled. We also get state-of-the-art results on MPIMF 3D-HP. The usual training and evaluation protocol on this dataset uses scale-normalized skeletons. We evaluate both the scale-normalized and the unnormalized raw poses. We evaluate absolute poses on the MUPOTS 3D dataset and also obtain state-of-the-art results in absolute and in root relative coordinates as well. Our approach also won this year's 3D Poses in the Wild challenge at ECCV. For this, we trained MATRAPS with a ResNet 101 backbone on several datasets and applied 5-crop test time augmentation. In this visualization, the red skeletons are the reference and the blue-yellow skeletons are our predictions. Even with such challenging motions from 3DPW, we can see that the scale and distance estimation remain relatively stable over time, even for unusual poses. Note that there is no temporal smoothing here. On this sequence, we can see robustness to occlusion and truncation. Even when the person detector gives us a partial crop, the prediction contains all joints. Our method is fast, since it only requires evaluating a standard backbone and can work with high stride values. With batching, we can evaluate more than 500 crops per second, so it's efficient even in multi-person scenarios. Our code is publicly available and is very easy to use for downstream applications. The model is a standalone TensorFlow 2 safe model without any further dependencies. Just supply the image, the intrinsic matrix, and the bounding boxes. And you get back the estimated absolute poses. So in summary, we presented a method to learn metric scale 3D poses end-to-end using heat map representations. The model can guess joints outside the image bounds and doesn't need the focal length for root relative estimation. But when we do have the focal length, we can also estimate the absolute non-root relative pose. It's fast and obtains state-of-the-art results on several benchmarks, including the 3DPW challenge. For more details, check out the conference paper or the extended journal version. Both are now available online, and you can use these QR codes to get the archive link. So, thanks for watching, and also thanks to my co-authors.